Now this lesson, what we are going to do is that we are going to examine how pressure in liquid actually behaves. So for example, if now I have an open cylinder and I put liquid in, and I wanted to find out what is the pressure exerted by the liquid at the base of the cylinder. Okay, I want to know what is the pressure. Now in this case, then the pressure at the bottom here would be experiencing a force over the area, which is here. Now what is this particular force that this area is experiencing? Well, the fluid on top has mass, and that means it has weight. So basically what is acting on the bottom of this cylinder is the weight of the liquid. So actually we can rewrite the equation to be this. Now before I carry on developing this equation, what I'm trying to do here is to show you how do we arrive in an expression that will tell you the pressure exerted by a liquid fluid. Okay, so let's carry on. So the weight is given by the weight of the liquid is given by mass times gravity, right? Yeah. Now what we are going to do is that we are going to look at the mass in terms of density. Yeah. So what we know is that your density is given by mass times volume. So this symbol here is called rho. It is the symbol for density. Now since we know density is universal, is a constant, is a property constant, then the mass of this can be given by density times volume. So far so good? So once we have that, we can rewrite our equation as this. Now if you remember, the volume of a cylinder is given by this equation, right? Volume is given by cross-section area multiplied by the height of the column. So for example, if now my liquid column is like a cylinder, then I just need to take this area and then I multiply by the h, the perpendicular h to the base, right? So if I know that, then this formula would become like this. Now what you notice here is that after we manipulate this, can you see that the cross-section area, the A, will actually get cancelled out? So because of that, we actually make use of this formula, rho GH. So this pressure formula is for pressure exerted by a certain liquid column. It is equals to the density of the liquid multiplied by the gravitational strength and the vertical height. So for example, if you are swimming in a swimming pool, let's say the swimming pool get deeper and deeper and you are swimming down here. When you are swimming here, you are actually being pressurized by the fluid on top of you. So of course, if you dive deeper and deeper, you can see that, okay, on top of you there are more and more layers of water. So if I wanted to actually find out what is the pressure that you are experiencing, I can just take the density of the water, multiply by the gravity, and finally multiply by the h measured from the surface. Now, is this the total pressure that you are experiencing? Well, let's take a look. For example, if you are standing on a flat ground, are you experiencing any pressure? In fact, yes. On top, around you, there is fluid. So what is fluid? Fluid can be any liquid or gas. So around you, there's air from the atmosphere. So actually, you are actually under a lot of pressure. The pressure acting on you by the atmosphere is equals to density of the air multiplied by G and multiplied by the thickness of the entire atmosphere to the sea level. So if you multiply all these things together, the atmospheric pressure is about 100,000 Pascal. So you may be asking me, wow, we are under so much pressure, how come we are not feeling it? Well, there are two reasons. The first reason is that inside your body, there's gas as well. So in your gas, there's in your lung, there's pressure. So what happens is that this pressure actually balance off with the pressure outside. What happens if your lung does not have enough pressure? Then you'll be squashed. The other way around is also true. If you are flying on a plane at a very high altitude, the Because if you are flying very high, that means the thickness of atmosphere on you is very little. So actually, the higher you go, the lower the atmospheric pressure. So I mean, if you have here this phrase that if you are flying a plane, the chamber inside the plane is actually pressurized. Why? Because if you are flying on a plane at a very high altitude, the surrounding pressure around the plane is actually very low. And if we do not keep the cabin pressure, you will find that your body's pressure will be larger than your surrounding pressure, and of course your eardrum will not be feeling very good. So similarly, if you are diving in water, what happens is that the surrounding pressure, the outside pressure will be higher than your body's pressure that's inside. So your eardrum will actually get pressed inside. So you will feel the pain. Similarly, when you are taking off on a plane, the surrounding pressure will be actually lower than your inner pressure, your body pressure, and then your eardrum will be popping out. So either way, if you don't equalize the pressure, you will feel your ear will be sensitive enough to pick up the change in pressure. Another reason for why you are not feeling this 100,000 Pascal from the atmosphere is because you are born into the atmosphere. So when you are born, and because our body structure has evolved to actually adapt to this kind of pressure, you don't feel it. But if you dive deep into the water, your body is not conditioned to do that, and you will feel the pressure around you building up. So technically speaking, even if you are standing on a flat ground, you are under 100,000 PA. So if there's a question asking you what is the pressure that you are feeling when you are under a certain liquid level, you have to add in the atmospheric pressure. So actually, when you are diving, your body is actually under this amount of pressure. Okay, now that we know that your fluid pressure is given by rho GH, you will notice something that is very interesting, that in this formula there is no more A. This means that if you have two cylinder, one big, one small, and you fill it up with the same amount of fluid of the same density, and if you are standing below, regardless of the cross-sectional area, whether it's big or large, as long as the density is the same and this vertical height is the same, both of them will actually have the same amount of pressure acting on them. Now this is also true if you have like a super weird kind of cylinder like that. As long as you fill it up till the same height, the pressure underneath will be the same because the pressure of a fluid column is defined by rho GH. So for example, if now I have this, and if I have this, if I fill it to the same column and you are underneath here, will PE and PF be the same? Yes, they will be the same, because as long as the vertical height here is the same, then according to rho GH, if the density is the same, G is the same, H is the same, then the pressure experienced by the bottom is also the same. Okay, so now we are back to the worksheet 7.0. Page 4, basically for 6A, this question is to actually ask for you to consolidate how do you change P equals to F over A into the liquid pressure formula, P equals to rho GH. Now, is this tested? Lucky you, this is not tested. Will it be good for you to know? Yes, it's good for you to know. So down here, I will just put down so that you don't need to flip in your book how it is being developed. So it is like this, W over A, W it becomes mg, and then the m become density times volume, and then after that it become volume become AHG over A. So finally it will become rho GH. So down here I have given you all you need. So this to here, this is because is density is equals to mass over V. Then after that, down here This is because V is equals to AH. Okay, so I give it to you. Now from this formula, so what you need to remember, okay, maybe that's more important. What you need to remember is P equals to rho GH. This is not for solid, this is for fluid only. That means liquid or gas. So if you look at this formula, you will notice that the pressure for your exerted by your liquid or fluid depends on only three things: the density of the fluid, the gravitational strength, not gravity, but the gravitational strength. Oops, sorry, I spelled wrong. Gravitational strength, and finally your vertical height. Not just height, but vertical height from the surface of the fluid. Okay, it does not depend on your cross section. It also doesn't depend on, for example, your slant height. So you may ask me, what is slant height? Well, for example, if you do this, and then if you do this, if you do this, and then if you do this, if the liquid level is the same, then the pressure underneath is the same. Okay, so it does not depend on this thing. This is called slant height. What is called vertical height? Vertical height is this. Okay. Then we can try to apply our understanding down here. Now, if you take a look at this, you will see that it is submerged and all that. I have to find the net force acting on the block. So if it is on Earth, then of course the block will be attracted by the Earth. You will have a weight, and as you can see here, there's a pressure acting on this surface. So therefore, there will be a force here. Your force is equals to the pressure multiply the area. That is because P equals to F over A, right? So similarly, underneath here, there will also be a force over here, which is equals to PA. Now, however, this pressure will be different because for liquid, the deeper you go, the higher the pressure. So because of that, let's call this F1 equals to P1. Then after that, here is F2 equals to P2 times A. So since the A is the same, I just treat it as the same. So how do we do the net force? We have to choose one direction as the positive, right? So I will just take, I don't know, let's take upward as positive, okay? Upward is positive. So here you go, I have my F net. F1 is going down, so it's minus F1. F1 is going down, yeah, minus F1. The weight is going down, minus W, and then plus F2. So my job is to actually find out what is the net force. So now I'm trying to find out minus P1A minus W plus P2A. Now I just need to substitute all the things that is inside. P1 is basically the fluid pressure exerted by this, right? So it will be rho GH1 times A minus the mass is 20, so this will be 200 plus rho GH2A. So far so good. So basically this pressure that is acting on the top side of the block is given by rho GH. And then after that, under the bottom, there will be pressure from the fluid, and then it will be also given by rho GH. So now what you can do is that you can put in all the numbers that you need. Density is 1000, so I have minus 1000 times 10 times A. Okay, A is 25 cm square, so I have to change. 25 cm square is kind of like 1 cm times 25 cm, right? Sorry, my cm square conversion, I need to do it step by step. So 1 cm is about 0.01 meter. 25 cm is 0.25 meter. So if I do that, I can actually convert my cm square to meter square. Doing this, it will be 0.0025 meter square. So now I have this. I can then put it in here, 0.0025 minus 200 plus 1000 times 10. Oh, I forgot the H. Sorry. That's the H. So now I need to put in the H. H is 0.05 here. then here I would have 0.0025, and the H would be 0.07. Yeah, so if you calculate this, you will get a final reading. Make sure that it is 2SF. Okay, this final reading, I'm not sure is it plus or minus, but basically this question is to test you whether you are aware that this pressure is can be expanded to rho GH. Okay,